Alrighty, now we'll go through some of the examples that we could not get to during lecture. So this example states, suppose block A has mass ma and coefficient of static friction is mu sub s. What is the maximum mass that block B, what is the maximum mass of block B before the system starts to accelerate? So we want to find how heavy can this be made before this system starts to accelerate up the ramp and downward here. So the approach is to draw the free body diagram for each of the masses and then use Newton's second law. So if I circle block A, I identify that it makes contact with the surface here, which is going to provide both a normal force and is going to provide some kind of frictional force at the surface. And then we have our long-range force of gravity. So when I draw the free body diagram for block A, also it makes contact with the rope here, which provides us with a tension force. So we've got tension pointing along the rope. Then the normal force is perpendicular to the surface. So that would be like so, because basically if we imagine that this is the this is parallel to the surface of the slope that this thing is on, the normal force makes a 90-degree angle with that surface. Then we have force of gravity acting straight downward. And then finally we have force of static friction that is going to keep block A from accelerating up the ramp from the tension force. So force of static friction pointing to the left. And the reason why I labeled this as a force of static friction is we're trying to basically get to the point of making mass be as large as we can before the system starts accelerating. So we're trying to max out this force of static friction by making mass B as large as we can. And that connection to mass B is through this tension, because if now we draw a free body diagram for object B, basically the only contact to mass B is the tension force, which is pointing upward, and force of gravity, which is pointing downward. Now, I'm going to use the convention where the block A, we use a coordinate system that where the x-axis points along the ramp and the y-axis is perpendicular to the ramp, and for block B, we can use our usual coordinate system. And if you'd like to use positive down and negative up to stay consistent with positive acceleration to the right equating to positive acceleration downward, that's perfectly fine. But what you'll notice is we're trying to figure out before the system even starts to accelerate. So since we're going to be assuming these blocks stay in equilibrium, this convention doesn't end up being as important in the calculations. Okay, so at this point I want you to pause the video, and I would like you to write the sum of the forces and try to calculate how big we can make MB such that this system stays at rest. So once you've done that, I'll go ahead and show the work up here. So if we do the sum of the forces in the x direction on block A, basically you have tension pointing to the right. We have force of static friction max pointing to the left. Then we also have a component of Fg. So as we saw in class today, in a coordinate system where we have a tilted coordinate system, we can figure out that this angle here is theta. So the x component of force of gravity is basically minus Fg sine of theta. And then that equals mass of block A times acceleration of block A in the x direction. Now, we're actually trying to get to the point where friction is maxed out, but the object remains in rest. So we're actually going to set this acceleration to 0. And now we have tension minus force of static friction max minus Fg sine theta. So force of gravity on block A, so I'll give that a subscript. Block A is pretty much ma times g times sine of theta equals 0. So that is the sum of the forces in the x direction. Now we know force of static friction max depends on the normal force on this object. So we need to use the sum of the forces in the y direction to figure out that normal force. So let's move this aside. Now let's take the sum of the forces in the y direction for block A. So sum of the forces in the y direction for block A is equal to, we have normal force pointing upward in the slanted coordinate system, and we have minus Fg cosine theta pointing downward, and since this block is not jumping off the ramp, this definitely, the acceleration in the y direction is 0. So this essentially just tells us that the normal force is equal to Fg times cosine of theta, and this is Fga, so that is equal to mass of block A times g times cosine of theta. Alright, now we've used the sum of the forces in the y direction for this block. We still have the sum of the forces in the y direction of block B to help us out. So now working with block B here, sum of the forces in the y direction is just tension. And if we keep the coordinate system where down is positive, up is negative, basically this sum will be force of gravity in the positive direction minus tension equals 0. Now remember earlier I said because the acceleration is 0, the choice of this coordinate system actually doesn't matter. That's absolutely true, because if I make this one negative, this one positive, there's no overall change in what this equation is telling us, because the equation just tells us that FGB is equal to the tension force. This is for block B. So the tension force is equal to mass of block B times acceleration due to gravity. Alright, now we have all the equations we need to solve for what we're being asked for. And in this case, it's what's the maximum mass of block B. So I will go back to this equation and plug in both the normal force into the expression for friction and the tension force here. So let's plug things in. So the tension force is just mass of block B times gravity. And note that we've taken force of friction to be its maximum value, because we're trying to make mass B as heavy as we can without the system accelerating. So this is minus mu sub s times the normal force on block A minus mag sine theta equaling 0. Okay, let's go ahead and plug everything in and rearrange things. So mbg is equal to mu sub s times mag cos theta. Notice that I essentially plugged in NA being equal to mag cosine theta there, plus mag sine theta. So going from this step of algebra to this step of algebra, I have moved both of these terms to the right hand side, and I've plugged in the fact that the normal force is equal to the expression here. Make sure that you are able to do this algebra on your own without looking at the details of my work, and check your final answer. So finally, mass of block B, pretty much I need to divide both sides by a factor of g, and what you'll see is the g actually cancels out from each and every one of these terms. So the maximum that mass of block B can be is mu sub s times ma cosine of theta plus ma sine theta. And overall, we should make sure that this makes sense physically. So let's take different limits. when MA gets really large, so we're keeping this angle constant, but basically when MA gets very large, both of these terms are positive and they increase in magnitude. Therefore, the maximum mass B I need also increases. Basically, to support a heavier weight on this side of the ramp, I'm going to need a bigger weight, counterweight here for mass B. On the other hand, also, apologies, I've accidentally switched this subscript from S to 0. That's F. Sorry, the last video got cut off a bit early. Let's discuss the effect of friction on this ramp. So if this ramp were frictionless or if this ramp were very smooth and so was the block, meaning the coefficient of static friction was very small, in that case, you wouldn't have to work against friction as hard to basically get block A to slide up the ramp. So static friction is opposing the direction of possible motion, which would be up the ramp in this case. So if this block ends up being very smooth, so μs is low, that means that I don't need as heavy of a mass block B to get mass A to start accelerating. On the other hand, when the coefficient of static friction is high, meaning these are rough surfaces that we're working with, when this is large, I would need a much larger mass B, to overcome the force of static friction that is resisting the acceleration of the block up the ramp. Alright, so that concludes this example.